Hello friends, till now in metric spaces we have studied the introductory concept in metric space, then complete metric spaces, continuity in metric spaces. Today we will start the fourth topic, compactness, compact metric spaces, and firstly we will study Heine-Borel definition of compactness. So it depends on covering of metric space, open covering, then subcover, finite subcover, etc. So for that, first we will define concept of cover, then open cover, finite subcover, etc. Okay. So a definition. Covering or open just cover. Let Xt be metric space and C be collection, then collection C of subsets of X, C of subsets of X is said to be covering or cover of X if union of A alphas belongs to C is equal to X. Moreover, subset C dash of C is said to be subcover of X if union of A alphas belongs to C dash is equal to X. It is known as subcover. Subcover of X from C. Moreover, if is subset in C is open subset of X, then C is called as open covering of X. Opening covering of X, and if C dash contain finitely many subsets, finite number of subsets from open covering C, of X, then C dash is called as finite open subcovering of X from C. Depending on this, we'll define concept of compact metric space. Compact metric space. A metric space XD is said to be compact if every open covering of X, every open covering of X has finite subcover for X. This definition is known as Heine-Borel property of metric space X3. Okay. So this is nothing but Heine-Borel property of X. A subset A of metric space XD is compact if AD itself is compact. If AD itself is compact. Then that A is called as compact subset or compact subspace. Example, show that RU is not compact. RU is not compact. So, what is definition of non-compact? A metric space is not compact if there exists some open covering of X having no finite subcover for X. Okay. Negation of this statement. If you are able to find at least one open covering of X such that if I take any finite subcollection from that C which doesn't cover X, then we say that X is not compact metric space. So, to prove RU is not compact, we have to construct some open covering of RU in such a way that from that open covering, if I take any finite subcollection whose union is not equal to X, that is our aim. So, here if I take say minus n to n example, C is equal to minus n to n belongs to n. Is collection of open subsets of RU such that union of minus n to n belongs to n is equal to RU. Therefore, C is open covering of RU. From this, if we take any finite subcollection, let C dash is equal to say minus nk k equal to say 1 2 dot dot up to r be finite subcollection from C, be any finite subcollection from C. Then if I take NP is equal to say maximum of N1 N2 up to NR belonging to RU is such that NP doesn't belongs to union of minus NK k equal to 1 to n, k equal to 1 to n, and therefore union of minus NK k belongs k equal to 1 to n or k equal to 1 to r, here I have taken, is not equal to RU. For any finite subcollection C dash of C, and therefore open covering C has no finite subcover for RU. Therefore this implies open cover C of RU has no finite subcover for RU, and therefore RU is not compact. RU is not compact metric space. You can construct so many open coverings. If I take next example to be, say, open interval 0 to 1. Okay. So that open interval 0 1 with respect to usual metric is not compact. So you have to construct some open covering for open interval 0 1 having no finite subcover. So we'll try to construct some open covering for 0 1. So consider C is equal to collection of 0 to 1 minus 1 upon n plus 1, n where is in n. Now here if you observe, what is your A1? Say if I take ANs is equal to this one. What is A1? A1 is nothing but 0 to half. What is A2? So this will become n upon n plus 1. Okay, this is nothing but 0 to n plus 1 minus 1, that is n upon n plus 1. N belongs to n. So we'll get half, then 0, 2 upon 3, 0, then 3 upon 4, and this values goes on increasing. This values goes on increasing. Okay. As n tending to infinity, this n upon n plus 1 approaches towards infinity, approaches towards 1. Is it right? So A1 is subset of A2, is subset of A3, and so on, are such that limit n tends to infinity of an is open interval 0, 1. Okay, as limit of 1 minus 1 upon n plus 1 is 1 as n tends to infinity, and therefore union of ans, or 0 to 1 minus 1 upon n plus 1, n is equal to 1 to infinity, this must be equal to open interval 0, 1. Implies C is 0, 1, where each an is equal to 0 to 1 minus 1 upon n plus 1 is open interval, and hence open set in open interval 0, 1. Therefore, C is open covering of 0, 1. Open covering of 0, 1. Now, if I take finite subcollection, okay, let C dash is equal to say an1, an2, and so on, an k be finite subcollection collection of C. Then for NP is equal to maximum of n1, n2 up to nk. If I take 1 minus 1 upon np plus 1, this belongs to 0, 1, is such that this is my x, is such that x doesn't belongs to union of an r is equal to 1 to k. So it is member of 0, 1, but it doesn't lie in this. It doesn't lie here. This implies C dash is not, C dash doesn't cover open interval 0, 1. Implies C dash doesn't cover open interval 0, 1, and therefore any open covering of, which implies any open covering, or therefore open covering, not any, open covering C of 0, 1 has no finite subcover, for 0, 1. and therefore 0, 1 is not compact. 0, 1 is not compact. If you take next example, let XD be discrete metric space, standard discrete metric space. Discrete metric space where X is infinite. So that XD is not compact. XD is not compact. Solution: we know every singleton subset of XD, is open set in X of discrete metric space is open set, and therefore C is equal to singleton X varies in X is open covering of X such that union of singleton X size I equal to 1 to n is not equal to X, as X is finite. As X is infinite. This implies open covering C has no finite subcover. Open covering C of X has no finite subcover. And therefore discrete metric space, infinite discrete metric space XD is not compact. Therefore infinite discrete metric space XD is not compact. Is not compact metric space. So in this lecture we have studied definition of covering, open covering, subcovering, finite subcover, and depending on that we have taken Heine-Borel definition of compact metric space. A metric space XD is said to be compact if every open covering of X has finite subcover. If you are able to find at least one open covering of X having no finite subcover, from that open covering if I take collection of finitely many subsets, whatever that collection may be, and if its union is not equal to whole set, then that open covering has no finite subcover. In that case we will say that that metric space is not compact according to this definition. So with this discussion we will stop this session here. Thanks for listening lecture carefully. Bye bye.